My name is Robel Campbell, and I'm a principal security researcher and lead of the APG's threat research team. I wanted to take some time and record a video for you all demonstrating some of my methodology while reverse engineering malware using the Cicada3301 ransomware. I'll go over a bit of static analysis using Iterative and some code analysis using x64 debugger. The goals here are to extract an embedded executable and also discover the key parsing function used to run the executable and try to figure out what makes this a difficult sample to execute. Cicada also shares some similarities with the Black Hat ransomware, and Morphosec did a pretty in-depth write-up on this if you would like to dive deeper and check out some more features of this ransomware. So without further ado, let's go ahead and dive in. We'll go ahead and start here by finding a sample that we can download and begin reverse engineering. I found a few samples here on Malware Bazaar. I went ahead and downloaded this first one already, so it's already saved to my desktop here. And this is the sample that we're going to be analyzing in this video. Now, when I begin my analysis or static analysis, I like to use a tool called Dissecting, or DIE for short. And what Dissecting does is it opens up a file and parses its headers to figure out what sort of file it is and the architecture and whether or not it's a executable file or maybe a text file, a PDF. It's a great tool to just get initial telemetry or just initial data, metadata about a specific file. I click the advanced checkbox here just to give me the complete set of options here. It's a pretty robust program and there's a lot of features that are available, but for this particular tutorial, I'm just going to focus on a few things. So first of all, I can look at the architecture here. This particular executable is a PE32 executable, which means it's a 32-bit architecture. And that can be critical to know because you might have certain tools that parse executable files and require a particular bitness or architecture. So there are two different versions of IDA Pro, 32-bit and 64-bit. 64-bit versions can disassemble 32-bit binaries, but not the other way. Another piece of information that I like to look at is the size. So this particular sample is rather large. It's in the megabytes. Usually executables are in the kilobytes. That's just something that is important to note when you're loading it into analysis tools. It can take a while to parse. Next thing I like to look at is the linker and compiler information down here. This one looks like it was linked with GNU linker or GNU linker. What this tells me is that this was probably cross-compiled on a different system. Usually if this was compiled on a Windows system, it would use the Microsoft built-in Visual Studio Code tools, but in this case, I think it was compiled on maybe a Linux system. We'll find out a little bit more about this later. Another quick triage tool that I like to use within Detected Easy is this virus total button. If we click this, it'll open up virus total for us with the hash of the binary. Here you can see that at the time of this recording, this is a pretty heavily detected binary. There's a lot of static signatures for it already, so antivirus products and EDR products will probably have no problem identifying this one. So now the next thing I want to do is open up this binary in IDA Pro. IDA Pro is a disassembler which takes executable files and disassembles them back into assembly language. Assembly code comes in many different forms. There's x86 Intel, ARM, and many others. But in this case, it's going to be x86 Intel format. So I'll go ahead and come down here. Before I open up the database that I've already created here, I'm going to go ahead and open up a different one just to demonstrate or show something that's kind of important when you're reverse engineering binaries. So anytime you're reverse engineering an executable, you want to enumerate as many symbols as possible. Now, a symbol is a plain English or plain text name of functions and variables within a binary. And what we'd like in every situation when we're reverse engineering malware or any software is to be able to have all of the original function and variable names within that executable. Something that's interesting about this Cicada ransomware is that it comes with debugging symbols called dwarf symbols. So when IDA loads this up, it says that dwarf info was found. So in this situation, we would click yes, it would open up the binary for us to do its analysis, and we would actually get debugging symbols. I'm not going to do it on this one since I already have a database open and it might take a long time to do the analysis. So I'll just cancel this. We'll go ahead and open up the database that I already have created. Let me go ahead and jump to the main function really quick. Okay. So here is our initial IDA screen here. This is what's called the IDA view. And what I have here is the main function of this program opened up. Back to what I was originally discussing about the debugging symbols. If you look over here in the function pane, you'll see that there are names for every single function in this binary. Let me go ahead and clear this filter so we can see all the function names. Usually when you're doing reverse engineering on malware, the symbol names and the function names will be stripped, meaning that the names will not show up. Instead, there will be a default name like sub underscore and then the offset of that function or the function's address in virtual memory. But in this case, we actually have all of the symbol names displayed to us. This is extremely helpful when doing your reverse engineering and analysis because it helps point you in the right direction for the goals that you have or the goals that you're trying to accomplish. Now, the main function is important because this is the start of the program. If you can identify the main function of a program, you know that this is where everything begins, and this will be helpful later on during dynamic analysis. So, looking at the main function here, you can see that it's pretty short actually. Looking down in the graph view, there's only one block here. Typically in a function, you'll see multiple blocks. Let's see if we can get an example here. Like this one, this has a couple blocks. Let's look for another larger function in here and see if we can get uh, anything. We'll just skip that for now, but go back to the main function here. There it is. So yeah, you can see that this is one block, meaning that There are no conditional jumps here. This is just one straight go at the instructions here. It goes down here, it calls underscore underscore main, and then that returns here to this move instruction, which transfers the offset of this function into this memory location and so on. But there's nothing else jumping here. This is the end of the program. So what we want to focus on is everything that's going on right in this area right here. And so we might look into this main function right here. However, this is actually not where the juicy information is. It's actually going to be right here. IDA is pretty good at changing the mangled symbol names for functions. So what that means is in C++ and Rust and other compiled languages, if there are functions that are overloaded or there's some polymorphism in the code, meaning that there's the same function name repeated multiple times in the code, you'll get a unique string value appended to the name of the function. And that just helps compilers or anything that is executing the binary to be able to find the specific instance of that function that's being called in the code. So built into IDA, there's some helper libraries that help deobfuscate some of that and help clean up the code. So we can see here the actual function is win underscore enc : main. So this looks interesting. This is probably something we want to focus on. Another thing we might want to do is try to figure out what was this written in. If you look at the article by Morphosec, it shows that it is actually written in Rust. Now, Rust is another high-level programming language similar to C and C++. If we would like to, we can actually come over here to our browser and take a look at the Rust programming language. This is their main web page. It says, why Rust? Well, for performance, reliability, productivity. So Rust gives similar advantages to C and C++, but one of the things that is really good at is compile time checking of safe code. So there's a built-in safety mechanism that prevents code from being introducing vulnerabilities like use after free vulnerabilities or buffer overflows. This isn't the primary reason why a malware author might choose this programming language. There are other mechanisms to this language that make it a little bit easier to use in terms of repeatable code and just available libraries that enable creating different components that the malware might need. So similar to, I'd say, Python or some other language that has a package manager, Rust also comes with a package manager and libraries in the form of what's called crates. And it uses the package manager called Cargo to download and install these crates. Now there's a lot of crates available. You can see here 157,000 different crates. So as you can imagine, a malware author is probably more drawn towards this language with the idea that there's so many easily available libraries at their disposal to carry out their tasks. So that's the Rust programming language in a nutshell. I'd suggest taking more of a deeper look at this programming language as malware authors are using it more and more. So let's get back to IDA. So how would you know that this was actually a binary compiled using Rust? Well, there's a couple of different ways, but the most simple way is looking for string values that contain keywords related to Rust, and it's typically only used with Rust. So we can go over here to the strings view, and as I mentioned before, Rust uses a package manager called Cargo. It's not typical for binaries compiled in any other language to have that keyword and embedded in the binary. So what we can do is perform a search for Cargo. It's not what I wanted to do. Here we go. And as you can see here, there's many entries here with cargo listed in the strings. When you install Rust and you build a project, if you use the cargo package manager to download and install libraries, depending on your operating system, it's going to store that library in your local user's home path or home directory. In this case, it looks like the user was in their root directory and the libraries were saved in this path, the .cargo registry source, and so on and so forth. You can also see the name of the libraries here. So in this case, it says regex automata, and then the version name for that library. Here's an RSA library, and so on. This is similar to examining malware's import tables. So we can come over here and we can look at the import tables, but that's only going to show us native Windows imports from other DLLs or dynamic link libraries. We're not going to actually see anything related to Rust in the imports table. So that's why it's important to come over to the strings and understand that Rust compiled binaries are going to include strings related to their imported libraries. Now, you could extract all of these and create a nice little list of all the libraries that belong to this. Now, I mentioned that one of the goals we had was to extract an embedded executable in this binary. So let's go back to the Morphosec article here. Scroll down a little bit. Right here. So in this section of the Morphosec article, it talks about how the malware uses PSExec with embedded user credentials to pivot between machines. So it says here, surprisingly, the compromised user credentials are embedded within the ransomware, and the PSExec is being executed with given credentials. Not a common thing in malware. You don't typically see specific user credentials embedded within the malware. Usually credentials are stolen or taken via other means and then used later, but in this case, the credentials had already been obtained and were within the ransomware. So if you don't know, PSExec is a sysinternals tool, part of Microsoft's suite of tools for administration on Windows machines. And what this allows you to do is use user tokens or credentials to access other machines and execute commands on other machines. It usually starts a service on that machine, and then whatever commands that you want to run will be executed. So what we're going to do is try and find where this is in the binary. PSExec has many signatures and will easily be picked up by antivirus, but this malware has hidden it somehow, almost in plain sight. So let's go ahead and take a look in IDA at where this is. Now, I already discovered where this was in the binary, and it sort of jumps out at you after taking a look at the layout of the binary itself. So let's go to the hex view here. And what I'm going to do is just scroll down through here until I see what looks like hex characters encoded as ASCII right here. So this is not a typical thing you would see in any binary, really. Let me scroll to the beginning of this. And this is a very large binary, as we saw before. It's about 17 megabytes. Another thing about Rust is that when you compile it, it contains all of the code required to run it. So any library files that are needed to execute it, it's all contained within the binary. So it's portable and it's easy to run on any system without any further dependencies. So that's part of the reason why this is such a big binary. All right, so if we look here, we have what looks like hex characters in the ASCII dump of this hex view. But if you look, the 4 here is encoded as hex 3.4. The D here is encoded as 6.4. So it looks like each ASCII character was actually being represented by its hex value within the binary itself. Another thing you'll notice here is that this is a very common magic bytes right here for a portable executable file. Every portable executable usually starts with an MZ. So 4D5A is MZ in ASCII. And so to the untrained eye, this might not stand out immediately, but after reverse engineering many samples, something like this would definitely catch your eye. So what we're going to do is extract this from the binary. And I'm just going to use a simple Python tool that I wrote to get the offset of this data and then basically carve it out of this binary and save it to another file. I've already done some of preliminary work for that. So the start offset of that data is hex 445494, and you can go ahead and validate that here. So I have this highlighted, and if you look down here, it might be hard to see, but it's the same offset right here. And then I scrolled all the way to the end of this and found that that offset is hex 5A2FB2. And so what we need is the length of the entire data. And to do that, we subtract the ending offset from the beginning offset, and that gives us this length right here. If we look over here, I've already done the output of the Python script that I wrote. But again, it takes an input file, so the file that we're carving, the offset or the beginning offset of the data we want to carve out, the length of that data, and then an output file. So I believe I already have, probably don't have. So we'll do Python carve.py -I will specify cicada. The offset, just copy the beginning offset here. The length that we calculated earlier. And finally, the output. We'll just call this cicada carve.bin. All right, so let's go back to our file explorer here, and you can see our file was saved here. Now, in its current state, all we did was carve out some raw hex data, but it's encoded as ASCII. So right now it's just individual characters here, but we need to convert this to hexadecimal characters so it's interpreted as actual raw binary data. One of the easiest ways to do that is to just open up a tool called CyberChef. And then we'll go ahead and open that file as our input file. So let's see here. Cicada carve.bin. Now we need to convert this to hex. So let's go over here and do, well, sorry, I take that back. We need to convert from hex. So what CyberChef is doing right now is it's thinking, hey, you just gave me this file and this is just some raw text of data here. I don't know how to interpret this data as is. So what we need to do is tell it to treat it like they're hexadecimal characters. So what it'll do is take every 2 bytes or every 2 characters here and treat it as a hex byte. So we'll go and use the from hex recipe. And as you can see here, the output shows that we have an MZ header here and also the DOS header of an executable. Now all we have to do is save this file, and we'll just call this ps exec. Windows Smart Screen. Keep the file. Okay. And now what we would do from here is take this file and actually try and validate that it's actually ps exec. You can do that using strings if you like, but just for the purposes of this demonstration, I'll go ahead and execute it. And you can see here we have ps exec, sysinternals, yada yada. And that pretty much confirms that that is what it is. We found the embedded ps exec executable. Okay, so now let's take a look at dynamic analysis. Usually when we're running malware or we're trying to figure out what malware does, one of the first things I do is actually try to execute it in a sandbox and capture all of its outputs. This is a little bit more tricky with this malware because it doesn't execute right away. It actually requires a key. So if I try to run this malware as is, I'll get a little error message here. It says key is invalid. What does that mean? If we look back at the threat analysis here, you'll see that there's command line options for this malware. So let's go back to the malware here and give it the -- help parameter and see what the options are. The first option or the first parameter for this is a key parameter, and it's actually a required parameter. Everything else is optional. If you like, you can set a specific path to be encrypted. You can tell this to sleep before performing the encryption, and there's some other stuff here. The key parameter is basically an encryption key that's needed to decrypt specific pieces of data within the binary before it can continue execution. So what we're trying to do is find out, where does this key reside? Is there any way to perform checks against the key and maybe patch all those checks to bypass needing the key to execute it? Or can we even run this without a key at all? So the next thing I like to do to figure that out is discover, where does the key parsing logic happen in the binary. In this particular case, it's very easy because we have debugging symbols, and the author of this malware did not obfuscate the name of the function symbols very well. So it was quite easy to find which function was responsible for this. So we're going to go back to IDA really quick. And I'm going to search for the function name, contains the word check in it. So this function, when in encryption check key and get rec text, after a little bit of analysis of this, I basically concluded that this function is responsible for decrypting essentially the ransom note and probably some other key structures of data within the malware. And then there are additional checks that are performed on that data to ensure that the data was properly decrypted. Now, earlier I had mentioned the size of a function in the graph view. So just to get an idea of how large this function is and how many conditional statements and jumps there are, we can look at the graph overview. It's rather large. There's a lot of conditionals in this that need to be evaluated and checked as it parses the key and performs decryption. So I'll go ahead and dock this again. Since we're using the 32-bit version of IDA free, it comes with a free decompiler. I'd much rather look at a decompiled version of this function than the assembly code. And what a decompiler does is it takes assembly code and it puts it back into the original source code as best as it can. IDA does a really good job of this. Tools like Binary Ninja and Ghidra also can do the same thing. So I'm going to go ahead and press the tab key here. Gives me this informational warning and then click OK. Now this looks more like a regular C or C++ function. Now instead of showing how to step through all of this logic and go through everything, I just wanted to give a brief overview of what this function does and where we would actually start our analysis. This is where the real reverse engineering comes into play and where you would have to identify key checks, rename variable names, and really try to get this function back to a state of its original form before it was compiled. One thing I will highlight here is some of the function calls within this. As we scroll through here, we'll notice several calls to functions that include cha-cha-20. Now, cha-cha-20 is a cipher for encryption. It's an algorithm that takes a key and a nonce and some data, and it performs several encryption steps in a very secure and fast way. It's actually one of the most popular choices these days for malware authors due to its speed. This is probably where they're accepting the key as the actual key for this algorithm and then decrypting the data. So the next thing we want to do now is try to find this function while we're dynamically analyzing it in a debugger. The debugger that I like to use is called x64 debugger. It has a 32-bit and 64-bit debugger. As I mentioned before, the architecture of the malware is important because you'll want to know which debugger to use. If you use the wrong architecture, the debugger will warn you of that and you'll just switch to the next one. So it's not that big a deal. So what I'm going to do is go ahead and search for x32 debug, the 32-bit version. I'm going to go ahead and open it up. Right. Now, if I'm reverse engineering a binary and I'm debugging it at the same time, oftentimes in the header file of the binary that we're analyzing, the base address will be listed and it'll be loaded at a particular address. Now, if you're loading it on a system that forces what's called address space layout randomization, or there's a flag built into the binary that forces address space randomization, it's not always going to load at that base address. Let's see if we can go to detect it easy and pull some of that info out here. So look here, if we look at the image NT headers of this binary, and then we look at the image optional header, under here you can see the image base address, which is hex 400000. If dynamic address space or dynamic rebasing was not enabled, it would load at this address base every single time. But that's not the case here. And so I can go ahead and show you in the memory map. Here's cicada.exe. And then here's this address, C80000. And this would more than likely change from execution to execution. Let's see if we can get that to change actually. Yeah, as you, let's go here. Actually, it varies from boot to boot, but in this case, it didn't load at that original base address of 400000. It's loading at C80000. So what we need to do, or what I like to do when I'm doing code analysis along with static reverse engineering in IDA or any disassembler, is I like to rebase the program in my disassembler. And in order to do that, all you have to do is come back to the IDA view. We go down to Edit, Segments, Rebase Program. And I'm going to set it to what we saw earlier, which is C80000. And hit OK. And what you'll start to notice here is that the analysis is rerunning again. And if we enable the addresses or the line prefixes here, we can see the actual addresses loaded up next to the function. You can also put this back into the linear mode. Scroll back to the top. And you'll see here that this has been rebased at C80000. The reason why it's showing hex 1000 is because the code segment, or the segment that where the code actually begins, starts at offset hex 1000 here. So what this does for us is it enables us to find specific functions that we've identified in our disassembler in the debugger. So just like before, when we found this check key and get rec_text, now we can find this function in the debugger. We know that it's loaded right here at this address. So I can copy this, copy the address. I can go back to my disassembler here. I'm sorry, my debugger. search for that address, and we're here. The debugger is not going to tell you what this is. All it knows is that there's assembly code here. There's no symbols loaded in a debugger, so it makes it difficult to understand where you are in the code and where it might be jumping. You can see here from prior analysis that I already have a breakpoint set on this function. And so the idea is to execute this until it hits the key parsing function and then step through that function to figure out how we can ensure that the code doesn't exit prematurely, or that the program doesn't exit prematurely, and that we successfully get it to run through its encryption routine and so on. Let's go ahead and try and run it and see what happens. Here's an entry point for the program, most likely the main function. And then we're going to go ahead and run again. And it looks like it's been terminated. You can see down here, the program has been terminated. Debugging stopped. So what this means is that between the start of the program and where my breakpoint was set, there was some additional logic being checked in the routines leading up to that point that caused the program to exit before we even got to our breakpoint. So we can just restart this, go back to our entry point. Let's go ahead and copy this address here and try and locate it here in IDA. So it looks like we're sitting here in the code. Let's go back to our debugger. Just step. Okay, so now we've jumped to this location here. Let's see where we are. So it looks like we're in the tmain CRT startup function. And this is just some more preliminary setup info for this process. You see here a call to get startup info. Here's a call to sleep. This is all just boilerplate code that's used to start a process and set specific environment variables and things needed for the process to execute accordingly. So we're not really interested in any of this stuff. So what we'd have to do next is kind of step through all of that code until we either return or jump to an entirely different part of the executable that's more interesting. There's something that's also interesting: indirect function calls. So you can see here, usually function calls are already denoted by a address, such as cicada dot, and then here's an address. And that's usually how function calls work. Or there might be a pointer pointing to a specific function. So for this case here, you can see there's a call to set unhandled exception file. That's because this has been resolved in the exports table of this binary. It knows where to find it. But other times, different functions don't have a specific address identified just yet. Maybe there's some table or virtual function table that has been set up, and you need to know, well, how am I going to call that function dynamically? It doesn't know where it's located. And so what it does is it dynamically finds a specific offset where that function might be located, and then it loads it into a register. In this example, it's EAX register, and then it calls it. So what we can do here is come over to the EAX register and see that this function was loaded here, and we can just go ahead and follow in the disassembler And now we're here at this function. We don't know what this is just looking at it, so let's go ahead and copy its address. Go back to IDA. All right, so it looks like we're in the dyn underscore tls init function. This doesn't look interesting at all to us, so we're just going to keep going. So as you notice that this is very an iterative process. Oftentimes you're just going to have to step through this until you get to the more interesting portions of the code, or you eventually find where this program exits. Now, I skipped a huge chunk of the analysis process. Oftentimes I would just start at the main function and I would look for something that's a bit more realistic or attainable, and that being, where are the arguments processed? Because before the function actually loads, it needs a key argument, and we never pass that in to the program. So let's go ahead and come over here and change the command line of this program. I already added this, but you could see here, it might be kind of small, but it's the name of the program and then the -- key argument. And then I just included a 32-byte key to get passed into here. You click OK, and then you can reload the program and continue doing your analysis. From here, I would look for where my argument is being processed. And I would step through every function until they got to the portion where the argument is actually being processed. As I mentioned before, this is an iterative process. You go back and forth between the debugger and the disassembler using the functions that have been identified with symbols, and then mapping those back to the debugger so that you can figure out where you are in the code. Now, something else that you can do in the disassembler is actually write comments. So these right here are comments. And if you want, you can also relabel these function arguments here, or these function calls or addresses to specific functions that have been identified in IDA. So you can come here and do label. So you can label the current address where the cursor is, or you can actually label the address itself as something that you've identified. These are just little tips and tricks that help with the analysis. And the cool thing about x64 debugger is that it saves your changes in a database associated with that file. So as long as you keep the file where it's located on disk and you reload that file, the same breakpoints will stay with it, and any modified variables or function names that you've changed in the executable will stay that way as well. So we didn't go through the entire portion of how we can patch everything. That would take a very long time, and I wouldn't say it's impossible, but the amount of variability in actually bypassing every check is pretty slim. It's very hard and difficult to do. Rather than focusing on that, it would be much easier to find a sample that has accompanying command line arguments that have been passed to it, or maybe the key was given with the sample. That way we can go ahead and just pass the key in and go from there. What I demonstrated today only scratched the surface of reverse engineering. I hope you guys enjoyed the demonstration, and if you ever have any questions, feel free to hit me up.